There is a real number that has two completely different names. The first name is 1. The second name is 0.9, with the 9s repeating forever. The first name is the one you have known since you were 5 years old. The second name is the one you have probably been told, at some point, is wrong. It is not wrong. Both names refer to the same number. The decimal 0.9, with the 9s extending into infinity, is exactly equal to 1. Not approximately, not in some hand-wavy limit sense. Exactly equal in the same way that 2 plus 2 equals 4. Most people, when they first encounter this claim, reject it. The rejection is so consistent that mathematics education researchers have studied it. Reddit threads, YouTube comments, calculus office hours. The same objection repeats. There must be a tiny gap, a microscopic distance, smaller than any number you can name, but still positive. There is no gap. The gap is exactly 0. This is not a trick of notation. It is a consequence of what the decimal expansion actually means, what the real numbers actually are, and what it takes for two real numbers to be different. This video is about why 1 and 0.9 repeating are the same number, the 4 proofs that establish it, why the human mind reflexively rejects all 4 of them, and what the entire affair reveals about the structure of the real numbers themselves. The first and most famous proof is so short it fits on a napkin. Almost everyone who has heard of this identity has seen this proof. Start by giving the mystery number a name. Call it x, so x equals 0.9 repeating. Now multiply both sides by 10. The decimal point shifts one position to the right, so 10x equals 9.9 repeating. The string of 9s after the decimal point is still infinite, so the number after the decimal point is still 0.9 repeating. Subtract the first equation from the second. On the left, 10x minus x equals 9x. On the right, 9.9 repeating minus 0.9 repeating. The repeating tails cancel. You are left with just 9. So 9x equals 9. Divide both sides by 9, x equals 1. But x was defined to be 0.9 repeating, so 0.9 repeating equals 1. That is the schoolyard proof. It is taught in algebra classes around the world. It is the proof most people first encounter, and it is the proof that most people first reject, because they sense correctly that something subtle has been glossed over. Specifically, the step where the tails of two infinite decimal expansions cancelled. Is that legal? The proof is correct, but to see why it is correct, we have to look at what the notation actually means. The second classical proof is even shorter. It uses a fact that everyone learns in elementary school. 1 divided by 3 is 0.3 repeating. You can verify this by doing the long division. 10 divided by 3 is 3, remainder 1. 10 divided by 3 again is 3, remainder 1. Forever. The decimal is 0.3. 3333. Now multiply both sides of that equation by 3. On the left, 3 times 1/3 equals 1. On the right, 3 times 0.3 repeating equals 0.9 repeating. So 1 equals 0.9 repeating. The proof is 2 lines long. It uses no machinery. And it is just as valid as the algebraic proof, because it relies on the same hidden fact, that infinite repeating decimals can be added, multiplied, and divided in the way we expect. But the fraction proof has the same flaw. From a skeptic's point of view, it assumes that 1/3 equals 0.3 repeating as an exact identity, not as an approximation. If you don't accept that 1/3 equals exactly 0.3 repeating, you don't have to accept that 1 equals exactly 0.9 repeating. So both classical proofs assume something about the meaning of infinite decimals that, if not justified, can be questioned. To settle the question, we have to define what a decimal expansion is. A decimal expansion is not a number. It is a notation for finding a number. When you write down 0.314, you are writing a recipe. The recipe says, take 3/10, add 1/100, add 4/1000. The result is a specific number. For a finite decimal, the recipe is finite and the result is exact. 0.314 is exactly 3/10 plus 100th plus 4,000ths, which is exactly 314 over 1,000. For an infinite decimal, the recipe is infinite, and here is where the subtlety lives. An infinite decimal is the limit of a sequence of finite decimals. Each finite decimal in the sequence is a specific number. The infinite decimal is whatever the sequence approaches. For 0.9 repeating, the sequence is 0.9, then 0.99, then 0.999. Each term is closer to 1 than the previous. The decimal 0.9 repeating is by definition the number that this sequence approaches, and the number that this sequence approaches is 1. This is not optional. The decimal notation is defined this way. There is no other reasonable interpretation. If 0.9 repeating means anything in the standard real numbers, it means the limit of 0.9, 0.99, 0.999, and so on, and that limit is 1. So 0.9 repeating, in any precise sense, is 1. Once we know what 0.9 repeating means, we can compute it from first principles. 0.9 repeating is by definition the infinite sum, 9/10 plus 900ths plus 9,000ths plus 9/10,000ths, and so on. This is a geometric series. Each term is the previous term divided by 10. For a geometric series with first term a and ratio r, where the absolute value of r is less than 1, there is a closed form sum. The sum equals a divided by 1 minus r. Plug in our values. First term a equals 9/10, ratio r equals 1/10. So the sum equals 9/10 divided by 1 minus 1/10, which is 9/10 divided by 9/10, which is exactly 1. Sum equals 1. This is a rigorous proof. No hand-waving about manipulating infinite tails. We use the precise definition of an infinite sum, the limit of partial sums, and the standard formula for a geometric series. The conclusion follows by direct calculation. 0.9 repeating equals 1. This is not an approximation, a convention, or a quirk of notation. It is the result of evaluating a specific infinite sum, which evaluates to exactly 1. Here is the part of the story that most explanations skip. The identity 0.9 repeating equals 1 is not a special quirk of the number 1. It is a feature of decimal notation that applies to every terminating decimal. Take any number you can write with a finite number of decimal places. 1/2, 0.5, the standard way to write it. But 0.5 has a second name. It is also equal to 0.4, followed by 9s forever. 0.4999 repeating, the same number in two notations. Take 0.25, the standard decimal for 1/4. It is also equal to 0.249 repeating, two notations, one number. Take 3.7, it is also equal to 3.69 repeating. Every finite decimal expansion that ends in any digit other than 9 has a partner expansion that ends in repeating 9s. Both expansions refer to the same real number. There is no other way for it to be. The number 1 is just the simplest example. 1 equals 1.0, which is the same as 0.9 repeating. 2 equals 1.9 repeating. 10 equals 9.9 repeating. This is how decimal notation works. It is not 1-to-1. Two different infinite digit strings can name the same real number. Once you accept that decimal notation has this two-name property, the identity 0.9 repeating equals 1 stops feeling like a paradox and starts feeling like a structural feature of base 10. One sork bunamai hesen. The most persistent objection to 0.9 repeating equals 1 goes like this. There must be a tiny number, infinitesimally small but still positive, that fills the gap between them. 0.9 repeating is 1 minus epsilon, where epsilon is very, very small but not exactly 0. To address this objection, we have to look at what the real numbers actually are. The real numbers have a property called Archimedean. It says in essence that there is no positive real number smaller than every other positive real number. For any positive real number epsilon, no matter how small, you can find a fraction 1 over n that is even smaller by choosing n large enough. So suppose, for the sake of argument, that there is a positive gap between 1 and 0.9 repeating. Call that gap epsilon. By the Archimedean property, epsilon is bigger than some fraction 1 over n, but 0.9 with n nines after the decimal point is already within 1 over 10 to the n of 1, and 10 to the n grows faster than n. So for any candidate epsilon, the partial sums of 0.9 repeating will eventually get inside the gap. This means the gap cannot be positive. There is no positive epsilon that fits, and the gap cannot be negative. 0.9 repeating is clearly not greater than 1, so the gap is exactly 0. The two numbers are identical. Despite 4 independent proofs, the identity 0.9 repeating equals 1 remains one of the most universally rejected results in elementary mathematics. The rejection is so widespread that mathematics education researchers have a name for it. They call it the persistence of intuitive resistance. What is going on cognitively? The first thing going on is that the human mind, when it sees 0.999 with dots, naturally interprets this as a process rather than a result. A process of writing nines forever. The process never ends. Therefore, the value, the mind concludes, never quite reaches 1. But the decimal notation is not a process, it is the result. The dots do not mean keep writing nines. The dots mean the value of the corresponding limit. That limit is 1. The dots are shorthand for a completed mathematical object, not a future computation. The second thing going on is the intuition that there must be a smallest positive number. The number line, in most people's imagination, is a sequence of discrete points. Between any two distinct points there must be space, and space implies a smallest unit. But the real number line is not like that. Between any two distinct real numbers, there are infinitely many others. There is no smallest positive real number. If you accept these two facts about the real number line, that points are dense and there is no smallest gap, the identity 0.9 repeating equals 1 becomes inevitable rather than weird. So what does this whole affair teach us? The first thing it teaches us is that decimal notation is just notation. The expansion 0.9 repeating is not a number. It is a string of symbols that, when interpreted under the standard rules of decimal arithmetic, points to a specific real number. And the real number it points to is exactly 1. The second thing it teaches us is that two different strings of symbols can point to the same number. Decimal notation is not one-to-one with the real numbers. The number 1 has multiple names. So do half and quarter and 3.7 and every other terminating decimal. The two-name phenomenon is a fixed feature of how we write numbers, not a defect. The third thing it teaches us is that intuition about the infinite is often wrong. The dots in 0.9 repeating feel like a process, but they are a result. The tiny gap feels like it should exist, but no positive number can occupy it. The real numbers, properly understood, are stranger and tighter than the discrete points on a line picture our minds default to. 0.9 repeating equals 1, not approximately, not by convention, exactly the same number, written two different ways. In the same way that 2 plus 2 equals 4, in the same way that 1/2 equals 5/10, in the same way that any number can have multiple notations, and the notations still refer to the same underlying object. It is one of the cleanest examples in mathematics of a true result that runs head-on into stubborn intuition. The intuition is wrong, the math is right, and the disagreement is what makes the question worth thinking about.